If your time series split is wrong, every metric is a lie. Fix it with a real rolling backtest. You will finish this video able to run a chronological, rolling evaluation that prevents future leakage and gives honest metrics you can trust. That clarity makes model choices meaningful and deployment safer. I'm Professor Pi, teaching AI foundations with simple Python. Rolling backtests matter because time is not IID. Data seen later often depends on data seen earlier. If you mix past and future when you evaluate, you get models that only look good on paper. In finance, energy, or demand forecasting, that mistake hides poor generalization and can cost money or bad decisions. Success looks like a stable estimate of out-of-sample error and a single next step forecast you can serve. At its heart, a rolling backtest is a set of chronological train and test slices. Think of a sliding camera that trains on what is visible and tests on what comes next. The camera moves forward one step, retrains, and tests again. Strengths are realism and prevention of leakage. Weaknesses include higher compute and less data per fold for small series. We will build a compact example that demonstrates that idea. You will see how scikit-learn's chronological splitter creates forward-only folds. Then, we will compute a naive baseline, train a linear model in a rolling way, try a fixed-size sliding window, and finally, run cross-validation and produce a one-step forecast. The code is small and uses simple lagged features, so the concepts stay clear. Now we will show the chronological splits. This snippet previews how scikit-learn time series split creates chronological folds without shuffling. It first builds a simple series Y that combines a linear trend with a small sign wobble, so forecasting is not trivial. The object TSCV is initialized with 4 splits, which preserves order and simulates rolling evaluation. The call TSCV.splitOnY yields train and test index pairs that grow over time, which we summarize as length tuples for a quick sanity check. Increasing n splits shrinks each test fold and increases the number of evaluations. The printed counts confirm strictly forward splits, which is essential to avoid future leakage. Next, we compute a simple persistent baseline across those folds. This example computes a walk-forward baseline using scikit-learn time series split to guarantee no future leakage. It prepares lagged inputs X and next step targets Y1 for later modeling, but here predicts each test window using a simple persistence rule. For every split from TSCV.splitOnY, the variable y-hat repeats the last training value across the entire test slice. The absolute differences against the true test values are averaged per fold, then averaged again into MAE0 to summarize baseline performance. Mean absolute error, which measures average absolute prediction error, is used here so we have a clear, interpretable yardstick. The printed naive MAE establishes a trustworthy yardstick to beat. Now, we will fit a simple linear model in the rolling framework. This code fits a scikit-learn linear regression in a rolling fashion using time series split. Linear regression is a basic model that learns a linear mapping from lagged features to the next value. It reuses the lagged feature X and target Y1, so the model predicts the next value from the previous one. For each chronological fold produced by TSCV.splitOnX, the function fit trains on past rows only, and predict generates out-of-sample estimates for the held-out block. The list errors collects absolute errors per fold, which are concatenated and averaged into MAE1 for a single reliability metric. Compared with the earlier variable MAE0, This approach should substantially reduce error by modeling the trend. The printed LinearReg MAE shows the improvement from learning structure. Next, we test a sliding window to emphasize recent data. This snippet enforces a sliding window using scikit-learn TimeSeriesSplit with max train size. The object, TSCVSW, caps each training slice to the most recent 8 rows, so LR.fit always learns from a fixed size, fresh history. The loop splits X chronologically, trains on the window train indices, and predicts on each test block, collecting absolute errors into errors 2 and averaging them yields MAE2, which you can compare conceptually to the earlier full history result. Increasing max train size lowers variance but may dull responsiveness. Decreasing it sharpens recency at the cost of stability. The printed windowed MAE quantifies the drift-aware trade-off you just introduced. Finally, we consolidate the evaluation and produce a one-step forecast. This example uses scikit-learn cross-val score with a TimeSeriesSplit CV to get a trustworthy overall MAE, then emits a next forecast. Cross-val score runs the model across the chronological folds and returns fold scores. And here, it returns negative mean absolute error values that we negate and average into CVMAE. After validating, LR.fit uses all available lag data X and Y1 and predict on the last observed value, produces the immediate next step estimate consistent with production usage. If you increase N splits, you obtain more fold estimates but smaller test blocks. Fewer splits do the opposite. The printed CVMAE and NextPred together provide a reliable metric and a ready-to-serve one-step forecast. Mapping this toy to a real project is straightforward. Replace the simple lag feature with richer lags and exogenous inputs. Use the same rolling logic when you evaluate on weeks of sales or minutes of sensor data. The mechanics do not change. Recap. A rolling backtest is chronological train and test folds that prevent future leakage. Use it when your data evolves over time and you need honest out-of-sample performance. One caveat is that more folds and smaller test blocks increase compute and can reduce per-fold stability. Next step, tune the number of splits and the max train size to trade off stability and recency. And watch how the validation MAE and next step forecast respond. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.